Okay, let's get started. Welcome to HAO Colloquium. Today we have Professor Axel Brandenburg from CU Nordita here to give his talk. Axel received his PhD in astrophysics from the University of Helsinki, working on solar dynamo and alpha effects. And then he was a Nordita postdoc and then an NCAR ASP postdoc for 2 years. Since 1994, he has held faculty positions in Nordita, University of Newcastle, Stockholm University, with which Nordita is now affiliated since 2007. And he's currently a visiting professor at CU Boulder, joint among 3 divisions or departments, maybe 2 days, 1.5 day each place. And since 2014, he has been a member of the Royal Swedish Academy of Sciences. He has a very broad research interest, mainly including the astrophysical fluid dynamics, dynamo theory, and turbulence theory, and also astrobiology with emphasis on homochirality, and which is a fascinating subject. Today, he will talk about magnetic helicity.
Thanks very much for your kind introduction, and it's a pleasure being back at HAO again. The topic of today's talk is magnetic helicity. It emerged as an important aspect in solar physics in the last 15 years. And it has important observational consequences that we have all known about from the photosphere, but it can even be measured in the solar wind. And the results are somewhat surprising, so that's why I will mention that also. Magnetic helicity, of course, has to do with the magnetic field. It needs to be generated. There's a dynamo process. This is the old picture from Parker, or something like that, where he was, for the first time, pointing out that the cyclonic events would be an agent that could create the poloidal magnetic field out of a toroidal magnetic field. The toroidal magnetic field itself comes from shearing a poloidal magnetic field. But once you have a poloidal magnetic field regenerated, it appears like the original one, but now at a shifted position. That's why you have a migrating dynamo wave. So this structure of the magnetic field resembles a little bit some folding of the magnetic field, some twisting, and that becomes evident also if you look at X-ray images of the sun. Even in the coronal mass ejections, you see features that resemble strongly the effect of twist in one way or the other, at least at a qualitative level. And magnetic helicity is basically quantifying what we see qualitatively. It is a measure of the knottedness of structures, magnetic structures. This very simplest example is one where you have 2 interlocked flux rings. But what really counts in the end are the crossings. Here we have one crossing, here we have another crossing. The magnetic helicity can also be mathematically defined as a volume integral over the dot product of the magnetic field with its vector potential, whose curl gives the magnetic field again. You can evaluate this integral over each of these 2 volumes where the magnetic field is finite. One is the volume phi V2. Here is the other volume, S1. Or S1 is a cross-section which enters in here. And the line integral is the part that you dot with A. And this line integral along this loop can be expressed again as a surface integral over the magnetic flux through that entire surface. And that one is given by the magnetic flux that comes through this second loop, through this first loop, and comes from the second loop. And therefore, we have phi2 times phi1, the product of these 2 fluxes. That's what half of the magnetic helicity is. And the second contribution gives another. If you were to reverse the sign of one of the loops, you would change the plus sign into a minus sign. Qualitatively, if we look at the surface of the here, for example, in EUV images of the sun, we see that structures, filaments, often somehow seem to cross with other filaments. And that is an important feature that allows you to qualitatively determine whether or not there is any kind of twistedness in it. So remember, I talked about the fact that helicity has to do with crossings. Here we have what looks like 4 different crossings, but in fact, the only difference between 1 and 2 is that the color of the one which goes from the left to the right is black here, and here it's white. In both cases, it lies on top of the other one. And therefore, the magnetic helicity of both of these structures is the same, and it's opposite to these 2 structures. If you now compare these filaments with our structure in here, you can see that we have a crossing where the one on the top is being crossed by one underneath, which comes from the right. And that gives you a positive contribution to the linkage. Here you have the same situation. You are on the top, you have somebody coming from the right, and again it gives you a plus. So this corresponds to positive helicity. And if you look at this previous image again, this was measured in the northern hemisphere, which I thought I said somewhere. Yes, 23 degrees north. And if you look here, this structure resembles this structure. Sorry, it resembles this structure, number 3. And so therefore, it has negative helicity. So remember now, in the northern hemisphere, we have negative helicity for these small filaments. Here are 2 other examples of a structure which in this case actually looks like it has 4 crossings, but you can undo 1 crossing because you can just shift, in this case, this loop from here slightly over there to the right without changing the topology, and then you would get rid of this crossing up here. So this would be the crossing that you would get rid of. And then once you do that, you end up with this structure, which is a well-known trefoil knot. And this one has 3 crossings. 1, 2, 3. And in all those cases, each of these crossings contributes with a minus sign to the helicity. Here is another example of an initial condition that was used in a numerical simulation. And you see the total helicity is, in this case, again, finite. And it's 3 times the product of the 2 fluxes. Or 3 times the flux squared. The flux is the same for each double crossings. Here is yet another example of a crossing where we have altogether 8 crossings. 1, 2, 3, 4, 5, 6, 7, 8. Now, in this case, there's equally many plus contributions as there are minus contributions. And so altogether, the total net helicity in this structure is actually 0. And yet, this structure is highly interlinked. And it's very difficult to undo that. So I said already, magnetic helicity is a conserved quantity. It changes very slowly. But in this case, we have a situation where the helicity is actually 0, and yet it looks like it will be very difficult to undo that. Numerical simulations have been performed by Simon Candelaresi and myself using such a structure as an initial condition. And after a short time, you see that this initially knotted structure begins to burst into 2 different structures that repel each other. And you see that in the spatial visualizations here. Here is one of the space coordinates, and here is time. And what is plotted is the local magnetic helicity density. And you see it really expels each other. What initially was 0 begins to undo itself and reorients again itself into a negative contribution in one part and a positive contribution in the other part, out of nothing to begin with. So in this case, it's an example of something that happens completely spontaneously, simply because such a knot structure is highly unstable. In general, we have situations where magnetic helicity is not the result of an instability, it is the result of explicit driving, like the cyclonic events that Parker envisaged back in his original paper. And that has to do with the fact that we have an external agent producing another pseudoscalar, which is here coming from the stratification and the rotation. In the northern hemisphere, they are anti-aligned. In the southern hemisphere, they are both aligned. And so the product of these, of the resulting vorticity with the velocity field is negative in the north and is positive in the south. So remember, I showed you the filaments were having negative helicity in the north. That agrees with the negative kinetic helicity. So these are different types of helicities. They are all pseudoscalars. They are one type of family. In other words, you can expect a pseudoscalar to be finite only if there is an external agent that like here, for example, that allows a pseudoscalar to be formed. In a completely symmetric situation, you might not necessarily expect that. So in other words, at the equator, you would not necessarily expect helicity. That is broadly true, but it's really not always true. I mentioned this for completeness, and the previous example was actually one such example. So here, out of nothing, you actually produced finite magnetic helicity. But in this case, it was spatially segregated. In this case, it is also actually possible to produce finite helicity, but what you do need is an instability. And so one of the examples that was studied by Piali Chatterjee shortly before she came here for a postdoc is an example of a horizontal magnetic field in the presence of gravity and no rotation. And in that case, depending simply on the initial conditions, she either gets a positive helicity or she gets a negative helicity. In this case, she didn't. She did, of course, measure the helicity in the flow, but she also measured the alpha effect. Such a structure produces an alpha effect, which I will come to in a moment. It produces large-scale magnetic fields, but even that one can have the two different signs of helicity just depending on initial conditions. But what you do need is an instability, something that drives you from very weak perturbations into something which is eventually becoming finite, and nonlinear interactions begin to play a role, and they lead to a competition between positive and negatively growing helical structures. You mentioned earlier the example of astrobiology that I was interested in, and in fact, in that connection, we have exactly the same conditions. In astrobiology, you have two ingredients. You have, or in the origin of life, you have two ingredients. One is called autocatalysis. That means the exponential growth of one species based on a substrate. So that is able to exponentiate the number density of a species of one particular kind. Now, both left-handed amino acids and right-handed amino acids are possible in principle, chemically. The difference is, of course, a very small difference from the fact that the electroweak force is violating parity invariance, but that is very, very weak, and so not important for any practical purposes. So both positively helical or left chiral and right chiral structures can both grow. Now, eventually, these two structures reach some kind of competition. Right-handed life forms begin to compete with left-handed right forms. And one of the two will eventually only win. And that is the one that actually, in the end, dominates overall handedness in the case of living organisms. And in this case, we have the same possibility. So again, there's two ingredients. One is exponential growth. That means you need an instability, and you need nonlinearity, which leads to a competition. For most of the rest of this talk, however, I will return to the usual situation where helicity is really the result of external driving, where we know in the north we have negative helicity in the velocity field at least, and positive in the south. However, I said already, magnetic helicity is a conserved quantity. So how can it be generated with a finite sign in any of the two hemispheres if it has to be zero? It was zero to begin with, and so it must be zero at all later times. So there's one possibility already. One was obvious from the plot previously. You can segregate helicities into different hemispheres or different locations. That's indeed one possibility, but another possibility is you can segregate it in wave number space. That means in length scaled. Here is shown the quantity that is called magnetic helicity spectrum. A magnetic helicity spectrum is defined in such a way that if you integrate over all wave numbers, you obtain the original magnetic helicity A dot B. This quantity, if you are in a periodic domain or in a closed domain, is a so-called gauge invariant quantity. That means if you add a gradient to A, which would not change the curl, this quantity itself would be unchanged. So it's gauge invariant for this or these two particular initial conditions, periodic and perfectly conducting boundaries. So finite or zero magnetic helicity means, and still something non-trivial, means that you can have different signs of helicity at small wave numbers and large wave numbers. Here in this case, we have at intermediate or small scales, I typically call it, we have positive helicity, which would correspond to the southern hemisphere. The length scales on which the magnetic helicity here is negative are very large length scales corresponding to very small wave numbers. That's why it is normally not directly associated with the original driving in the southern hemisphere. So this is the situation in the southern hemisphere, positive at intermediate length scales, negative at large length scales, such that the net is zero. The surface underneath here is equal to that over here. Such a result simply forms automatically once you twist a loop in the way that Parker envisaged in his original paper. You take an originally straight loop, you lift it, subject it to the effect of expansion in a stratified atmosphere and rotation. And the rotation is the one which leads to this twist. Now this twist shows itself as a negative helicity on the large length scales, but internally such a loop structure will be also attaining an internal twist, and that's the one which you see at higher wave numbers. Here's another sketch of this, how one can roughly imagine that happens. So you have an overall tilt, and once you tilt such a structure, you can never do this without imposing internally a twist in this loop.
Can you have more than one crossings, zero crossings?
Crossings?
Yeah.
So in this case, it is quality. So this would, in principle, have only half a crossing here.
I was thinking the spectrum.
Oh, whether you can have more zeros.
Yeah.
In principle, one can imagine such a situation, yes. And of course, we are talking about turbulence. Turbulence is not necessarily always very clean. So from that point of view, there would certainly be a random component that would allow you to have a more messy behavior at all length scales. So we should expect to see a clean signal after sufficiently time averaging only. But it is in principle possible, and maybe that's exactly what happens in the solar wind, because there will come mention some non-trivial behaviors where possibly higher number of crossings are conceivable. But they have not been studied or seen explicitly yet. Here's just another such picture where you then see that such looped structures even capture the imagination of advertisements, like in this case here, for example.
Maybe it's a candy maker.
Huh?
Maybe it's a candy maker.
And yes, it is actually, I think that has to do with traffic stuff. Anyway, so what we have now seen is that this concept of twist is something that Parker was not originally envisaging. Parker was thinking of a toroidal magnetic field that was lifted and produces a poloidal component that forms part of the large-scale poloidal field once it reconnects. In reality, you have internal twist, which is left-handed in the northern hemisphere and right-handed in the southern hemisphere. You have corresponding crossings or structures. This one would correspond to the north, and look at this structure. It's an inverted S, and it looks a little bit like an N. So it's easy to remember. N for north, if you see an N-like structure here, and south, which would be the mirror images of this in the southern hemisphere. So this is what you should watch out for. if you try to identify signatures of helical magnetic fields in magnetic fields on the solar surface. On one view graph, on this one page here, I will summarize research from at least a decade, where people have been trying to understand the importance of magnetic helicity to understand what was coined catastrophic quenching of the alpha effect. So the alpha effect is an effect that is allowing you to quantify what Parker envisaged in his original 1955 paper. Nowadays, we have the possibility of actually measuring the alpha effect. This has been done over the last 20 years, and the initial results were rather disappointing. They're also not really relevant, and that's why I spent only a single page on this. But the initial calculations assumed that the mean field that you define, and mean fields you define because you don't want to worry about small-scale fluctuations. You want to have a theory for explaining the large-scale poloidal loops and large-scale toroidal magnetic fields without looking at the individual structures that contribute to that. So you really do want to average over the constituents and get the final result out of a mean field theory. But if you define as a mean field a full volume average, then what you will find, relatively easy to see, and numerical simulations have shown that at large magnetic Reynolds numbers, this alpha becomes 0. So without knowing what was necessarily wrong with this idea, it was a disappointing result for almost a decade, and people really didn't know what to make of that. That was throughout all of the 1990s, roughly. However, if you relax the definition of a mean field to at least a planar average, so that means you average over 2 coordinate directions, for example, and therefore the result is still dependent on one direction, the whole situation changes. As an example, in this case, you could not even define a current density, because the current density is given by the curl of the magnetic field. But if the magnetic field is a constant, then the curl must be 0. And so it's a sort of meaningless Gedanken experiment here, because you have a large-scale magnetic field, you produce it against 0 currents. And so consequently, this magnetic field must be a conserved quantity, which it actually also is. And so therefore, one would also not have expected an alpha. So the situation changes immediately once you allow the average to be a planar average, or for example a one-dimensional average, like for example a toroidal average over this circumference of the sun. In that case, you can define a coordinate-dependent mean magnetic field. You can calculate its curl. In particular, you can calculate the so-called current helicity, the mean current dotted into the mean magnetic field, and this quantity remains finite. So alpha now itself turns out not to be 0. However, the difference between alpha effect and the part which corresponds to turbulent diffusion turns out to go to 0 under relatively simple conditions. So some signatures of catastrophic quenching still persist, in the sense that that even though you are able now to reach relatively strong or very strong mean magnetic fields at saturation, the time it takes to reach saturation is resistively long. So that might lead to a problem in understanding, for example, in 22-year cycle for the sun, if this was all it is. But fortunately, that's not the whole story either. And in reality, we have what is called magnetic helicity fluxes. And in particular, its divergence are different from 0. And that changes the structure, the whole situation even further. It leads to a relaxation of the fact that the timescales are very long. The timescales now become of dynamical order. And another important finding is that the type of fluxes, magnetic helicity fluxes, that have been identified in such systems are what we call turbulent diffusive helicity fluxes. And that means they are down the gradient of a local magnetic helicity density. So it's like temperature. You'd have a temperature flux, and the flux goes from hot to cold. Here you have helicity. It goes from strong helicity to weaker helicity. However, helicity is a signed quantity. So it can also be a negative, strong negative helicity. It would change, it would go towards zero. But it does not necessarily have to become zero, and that is one of the things we will see in a moment. Another important question that emerges is we are no longer talking about volume averages or periodic boxes, and therefore this quantity is not necessarily a gauge-independent quantity. Here is shown the sum of the two contributions to magnetic helicity, a contribution from small scales indicated by lower letters, and a contribution from the large scales indicated by overbars. So the sum of these two is something that should not change except for Spitzer resistive effects. And indeed, Spitzer resistivity is a term here. There is a contribution. This is a dissipation of helicity from large-scale fields. Here's the corresponding contributions from small-scale fields. The sum of these two gives something finite, but it is proportional to the magnetic diffusivity, which itself goes to zero in the limit of large magnetic Reynolds numbers. You have a production of magnetic helicity from the alpha effect, from the electromotive force, which is written here as immediately the sum of two contributions, alpha effect and turbulent diffusion. This gives E. However, the small-scale contributions are exactly equal and opposite to that what produces the large-scale magnetic helicity, and therefore no net is being produced. So the alpha effect produces a large-scale magnetic field, but it leads immediately to this penalty of producing equally much magnetic helicity of the opposite sign. And that is a quantity that can quench the dynamo. This is something I probably skipped over briefly when I showed this picture here. When I showed this picture here, I forgot to highlight this line here. So the alpha effect has to do with a contribution from the kinetic helicity, from the handedness of the cyclonic events. However, as you have finite magnetic helicity in the magnetic field also, that leads to an additional contribution to this alpha effect, which was identified first by Annick Pouquet and her collaborators at the time, all in Boulder back then at the time. And this leads to the possibility that alpha can in principle become small, if not even vanishing. And that just depends on how big this becomes. So coming back to this page here, this does not produce any net magnetic helicity, but it does lead to producing small-scale magnetic helicity, and that's a quantity that has a corresponding contribution in J dot B, that's different by wave number squared factor, and that is a dangerous one because it leads to the possibility of catastrophic quenching. And here's the contribution that can alleviate this catastrophic quenching, and these are the helicity fluxes. Now, let's first of all talk about the quantity of the gauge dependence. A dot B is gauge dependent. That's already difficult. Fluxes, in principle, are given by E cross A. They are also gauge dependent. However, if you are in a steady state, and if this quantity then happens to vanish in a steady state, statistically steady state, then this quantity has a chance of being vanishing. And once you determine it is vanishing, then you have three terms on the right-hand side that all must balance. Now, two of them are gauge independent. There's nothing about magnetic vector potential in these two quantities. And therefore, because two gauge independent quantities must balance this one, even the third term must be gauge independent, and even locally. So you can now for the first time talk about a magnetic helicity flux density locally, that it must be gauge independent under these particular circumstances of a statistically steady state. And so this is now a meaningful, physically meaningful quantity. You can determine them for different increasing Reynolds numbers. And what has been found is that the magnetic helicity flux divergence typically is a very small quantity compared to the other two terms. And that is very unfortunate. And therefore, this term has not yet any chance in being important in most of the simulations. And it's only at increasing Reynolds numbers, once you have access to Reynolds numbers well on the order of 1,000, if not bigger than that, that these magnetic helicity fluxes become, for the first time, at least comparable to the other two contributions. And only then the Spitzer resistive term becomes somewhat smaller than these terms. So what you eventually want to hope is to reach a situation where these terms are balanced against the blue ones and that the red ones are completely unimportant. And unfortunately, nobody has seen that yet. And it's only now, actually, that we begin to see how close or how far away we are from a solution to that.
Question. So here the transfer of helicity from the fluctuating to the mean field is gauge independent. Is that in general true?
Yes, you mean this one here? This is in general true, yes. Yes.
Yeah, even for spectral transfer and then.
Yes, yes, yes. That's right. There's even a contribution from the fluxes, which also leads to a cancellation. I will not mention that here, but just for completeness, there's a similar term that you can construct there. So not everything in the fluxes are necessarily bad ones. So the important conclusion is we have a chance in seeing the magnetic helicity flux divergence as being important, and these are gauge-independent quantities. So the lessons from dynamo theory now are twofold. On the one hand, magnetic helicity is no longer just a measure of the connectedness or the complexity of the field, as it has been often viewed in observational solar physics. It is a critically important quantity in dynamo theory. And so, therefore, we now want to confirm observationally whether we can see any signatures of magnetic helicities at large and small length scales in any of the observations. Now, magnetic helicity has been determined by a few people, but never the spectrum. So the spectrum has not received any attention until very recently. So therefore, we cannot really easily address the question whether we have opposite signs at different length scales. So this will be an important quantity to determine. One way of getting hold of the spectrum of magnetic helicity was envisaged by Bill Matthews some 25 years ago in an important paper where they applied in situ measurements of magnetic fields in the solar wind using the Voyager probes. What they had at their disposal was all the three components of the magnetic field at the location of the spacecraft at increasingly larger distances, as you know. But this was a spacecraft that was in the ecliptic, and so you might not necessarily expect a systematic sign. But the technique that they used was a very important one. They made use of the fact that the two-point correlation tensor, these are two different components of the magnetic field, Bi and Bj, shifted relative to each other by position r, could be measured if you picture the turbulence as a package that is passing by the observer. So if you consider turbulence being in this box here and being statistically the same all over the box, then you can measure different positions of the box if this box comes past the observer. And that is called the Taylor hypothesis. So that means measuring at different positions means just measuring at slightly shifted times. This is the standard technique that is being used in wind tunnel experiments, of course. So what we now want to do is we want to measure this two-point correlation function and then want to go into Fourier space. In Fourier space, under the assumptions of isotropy and homogeneity, this tensor has the following very simple structure. These must be isotropic tensors, and the only isotropic tensors that you can construct are delta ij, ki kj, these are the unit vectors of the wave vector, and epsilon ijk. And you get a rank 2 tensor by multiplying by another k. So this one is a antisymmetric contribution to the two-point correlation matrix. This one is a symmetric part. The symmetric part has a coefficient in front of it, which is wave number dependent, and it is equal to the so-called magnetic energy spectrum. And the second part is the same quantity that we defined earlier. It's called the magnetic helicity spectrum. So once we measure the correlation function, we can measure the energy, but in particular its spectrum, in particular its helicity spectrum. So this is a technique that we now have to use. And it has been used for the solar wind. It has, they found plus and minus indicated by open and closed symbols. If they're multiplied by k, they must be equal or less than the energy spectrum. That's why these points are all below the spectrum. The distance by how much they are below this energy spectrum tells you how much is the relative strength of helicity. And so they divided these two quantities, and they're all fluctuating around 0, but they are between plus and minus 1 each time. This I explained already. So what you have to do is measure two perpendicular components of the magnetic field, and the magnetic helicity is then given by the normal component and the third component, and both the helicity, both the Fourier transformed, and one of them is complex conjugate. So that's the quantity you can measure. Now, I mentioned the difficulty that you have to do this away from the ecliptic. And the only spacecraft that did that was the Ulysses spacecraft. Ulysses went in an orbit. It had different radii between 1.5 AU up to 4.5 AU. As it is further away from the spacecraft, the magnetic energy density decreases and approximately proportional to 1 over r squared. And so the quantity compensated by r squared is a quantity that is roughly independent of distance. Even that is not completely true, but it's roughly true. And this is, by dimensions at least, a quantity that corresponds to a luminosity. This can be measured. Here are shown the data without doing any averaging. So once you have the magnetic helicity spectrum multiplied by k, it must be below the energy spectrum. That's the case. But what is shown here is a modulus. If you divide the two by each other, then it's a quantity that is between plus and minus 1. Here we have clipped it between plus and minus 0.5. And if you average, then you see in the northern hemisphere a contribution that is negative at small wave numbers and positive at large wave numbers. So there is some indication that the helicity indeed has two different signs. If you average over broad wave number bins logarithmically spaced, you see, depending on which distance you are, here more than 2.8 AU and here less than 2.8 AU from the sun, you see in both cases two different signs. Positive in the northern hemisphere at large wave numbers, small scales, and negative at small wave numbers. So how does that compare with what we found in the solar wind? Remember, cyclones in the northern hemisphere have a negative helicity. So we expected at small wave numbers not only the kinetic velocity to have negative helicity, but also the magnetic field to have negative helicity. And that's not the case. It's actually positive. So have we done something wrong? Then there is indeed the possibility that all kinds of things can go wrong because, for example, if you define your Fourier transform the other way around, you can pick up a minus sign, a plus sign here. Or if you just interchange some other. So altogether, 3 different ways of in principle screwing up the sign. So after careful analysis, we came to the conclusion that these signs are actually the correct ones, and they are surprising. And so we went ahead and publishing that. But we were always worried. And at the same time, here, by the way, to complete the story, north and south really shows different signs. So here's the summary. What we see in small length scales from the dynamo should be positive. That's actually now for the south. But what we see in the solar wind has the opposite sign. So at about the same time, one of my PhD students did an experiment to understand the interaction between a dynamo and its exterior. So he had a simple dynamo where he had turbulence being driven in a spherical shell up until this radius, and the exterior was led to its own evolution. So it was being fed by magnetic fields that made it through this boundary, through what we often call magnetic flux emergence. So the magnetic field pushes itself through its own twist into the exterior. And what he did was measure magnetic helicity. And here's shown already J dot B. Close to the surface, it's negative in the south, indicated by yellow. However, at large distances, he finds mostly the opposite sign. If he averages, again, very clearly above the surface, there's the opposite sign. Negative in the southern hemisphere, and positive in the northern hemisphere. Here's a long time average, again confirmed. So what we now find in the solar wind, although we convinced ourselves that we did the right mathematics, it is now actually confirmed by a completely independent numerical simulation. And so maybe it's not incorrect after all. And so we have to look for that. In fact, we found earlier such indications already in another experiment where we had a negative helicity in the dynamo region and measured magnetic helicity in the exterior. We were here putting a lid. This was a z-coordinate in a disk-like dynamo. We were putting a lid in the domain, so that's leading to eventually the code crashing, which is why we'd never published this picture. And this is also showing these wiggles, but the sign of the magnetic helicity that was accumulating and was not being let out, that's why the code crashed, of course, was negative, was opposite to what we see in the interior. So how can you possibly understand that? We have two possible explanations. One of them is following qualitative picture. Remember, in the dynamo region, you have an alpha effect which dominates over turbulent diffusion. And let's look at the contributions from mean field and fluctuating field. And let's focus on the contributions to the fluctuating field. This is this equation that we saw in a very similar form already earlier. So now in the dynamo region, the alpha effect is an important quantity. It dominates over the turbulent diffusion. Alpha in the northern hemisphere is negative, and therefore produces negative. Alpha is positive in the northern hemisphere, but because of this minus sign, it produces negative helicity in the small scales, in the fluctuations. However, once you come into the solar wind, it also produces a large-scale magnetic field. Therefore, J dot B itself is positive, but this is the subdominant term in the dynamo region. However, now you come into the solar wind. In the solar wind, we don't expect the alpha effect to work, yet you have turbulent diffusion because the solar wind is turbulent, and you expose it to a magnetic field that had originally large-scale positive helicity. And so that would lead to an opposite sign, which now leads to a plus sign, a large wave in the solar wind region. This is one possible explanation. We are not sure about that. Another explanation is based on the fluxes. So now we think that we have a steady state here. Imagine a steady state. This is 0. And so all this has to balance against the flux. And this flux should be a negative gradient of the helicity density. So if you have a negative helicity, now you want to have a flux of this. This flux must have opposite signs. So this would not be 0 flux because there's 0 gradient. Here would be a positive sign, and here also. In both of these cases, it is heading towards 0 and is actually crossing the 0 line. And so in both of these cases, we expect as a function of height or distance from the surface, we might expect a change of the sign of the helicity. So this is the difference between temperature diffusion, where you can only go to 0 Kelvin. This is a signed quantity, so you can go through 0 and can actually, in principle at least, have opposite sign. So this is a second explanation. Whether that one is true or not, we don't know for sure. And so that is one of the things we have to study.
So on that same note, could you have an outward helicity flux that has a divergence in the domain and a convergence above the domain that leads to?
I think it would always have. It would have to have a divergence in order to have a constant flux.
Right, but I mean the helicity flux wouldn't have to change sign. The gradient of H could still be outward, but you could have a divergence of the flux.
Right. So you're picturing a situation. So the gradient must be, of course, like this. But you're thinking it is not crossing the 0 line, right?
Yeah, it could.
It could, yes. Yeah. So that's what I'm saying. It is not well understood. It is a possible explanation for something that we otherwise don't understand at all. And so any better explanations for that are certainly welcome at this point. And I think it cannot be all that hard, of course, to understand that. So finally, I will talk about using a similar method at the solar surface. So again, I mentioned magnetic helicity has been studied by a number of different groups, but the spectrum has never been looked at. And so the way to calculate a spectrum would be to use, again, Fourier transform. So that means you have to do a Fourier transform of your components of the vectors, of the different components of the vectors. And again, you can construct a two-point correlation function, which in wave number space has this form. It has a symmetric part if you assume, again, isotropy and homogeneity, which is a big if here. So you have two contributions, one from which is proportional energy spectrum, one to the helicity spectrum. And the helicity spectrum enters in certain off-diagonal components of this matrix, here and here, for example, whereas much of this is dominated by the magnetic energy spectrum. So both of these quantities can be determined, energy and helicity. Here's a result. This is a result for the southern hemisphere, and we see positive in red at these intermediate length scales, and here the energy and also magnetic helicity spectrum goes down, so not a big contribution. So mostly it's dominated by plus, and that is what we do expect in the southern hemisphere. Negative in the north, at small length scales, positive in the south. Here's a much more average spectrum, then you don't see all this noise. And it's basically well confirmed that you have a relatively strong helicity because these curves are not so far apart from each other in the northern hemisphere. So at the surface, we can reproduce a spectrum as we expected. In the solar wind, further away, we have the opposite. That means we need to find out the point where it actually changes sign. Here's, by the way, another active region where we see, for the first time, it's also in the southern hemisphere, but now there's a strong contribution from the opposite sign at already large length scales. So even here now, we begin to see two different signs. So the technique that I wish to look at in the future is a technique that is familiar from radio observations of galaxies. But the sun itself has been measured in radio wavelengths. What you see is that the corona is mostly Faraday-thick. Faraday-thick means that the amount of rotation, Faraday rotation that you expect in the corona is relatively large. The Faraday rotation has to do with the product of the magnetic field in the line of sight, the depth, the geometrical depth, the electron density, and a constant. So you do expect that the perpendicular magnetic field will rotate perpendicular to the line of sight as you go through a magnetized medium. If you now change the wavelengths enters in the integral, you will change the overall Stokes parameters, Q and U. And this has been measured. Here's a measurement from Westerbork at 6 centimeters. As they change the wavelengths very, very slightly, they have a very high resolution. They change it from 6 centimeters, or a little bit more than that, to 6.001. That is approximately one wavelength. They change this, the sign of the Stokes U parameter in this case. So Stokes linear polarization can be measured. However, it's extremely, extremely optically thick. One way to get rid of this is to go to shorter wavelengths. And there's another way of getting rid of this depolarization, and that is if the magnetic field itself, which enters here, this is the integral to the Stokes parameters. It has two contributions, one from the Faraday rotation, here from the intrinsic polarization. Now, this intrinsic polarization could be something which comes from a magnetic field that itself is helical. And if this magnetic field is helical, then this contributes to an angle phi that is rotating potentially in exactly the opposite way as the Faraday rotation is rotating. So you have Faraday rotation canceling to zero, but now the magnetic field itself can offset this rotation, so that all of a sudden you see finite polarized intensity. And that is shown here. Polarized intensity for certain wavelengths, lambda squared, can reach a maximum at finite wave numbers. That is what you would expect for a helical magnetic field. The overall technique is it's not well known for the helical case, but the fact that you can use this depolarization, it's not a disadvantage, not necessarily. It can be used to your advantage because you can, for example, invert the integral of polarized intensity and obtain an integral which is like the inverse Fourier transform. But it's a Fourier transform with lambda squared being the variable. And the difficulty, of course, is that negative lambda squareds cannot be observed. But this technique goes back to a paper by Byrne and is now becoming of extreme importance now that we can actually, for the first time, measure continuously through various wave numbers. These magnetic fields have all their certain signatures. Also, bi-helical magnetic fields have signatures in terms of different lines in the lambda squared spectrum. So what are now the corresponding lambdas that we should expect for certain wave numbers of the magnetic field? Here's a table there where we see various radio telescopes. The Jansky Very Large Array is between wavelengths of 0.6 centimeters up to 4 meters. This is a very, very large wavelength. And so we would expect very strong depolarization. That means it would not be of interest for wave numbers in the interesting range, which would be approximately like this, unless we have very low electron densities. And that means we have to go to very large radii in the corona. So with the Jansky Very Large Array, where you do have a large dynamical range, you have in principle the possibility of seeing the cancellation of depolarization from a helical magnetic field. ALMA is already better, but there are other telescopes on the horizon. CARMA has been the so-called combined array for research in millimeter astronomy is no longer working, but it was an array that had access to 1 millimeter wavelengths. And we will soon have the LAMA, the Large Latin American Millimeter Array, which brings us to 0.3 millimeters in wavelengths. And then we can see in the lower to somewhat upper corona, where the electron density is 10 to the 8 centimeter, and the magnetic field strength may be still 1,000 Gauss, we could see helical magnetic fields whose wave number is between 0.2 megameters to the minus 1 and 200 megameters to the minus 1. These are small length scales. These are large length scales. So these are possibilities that we might be looking at in the future. So the ultimate goal of this is to measure eventually the reversal of the magnetic field in the corona. So remember again, magnetic helicity is an important quantity, not just for the heck of it, as people have often been looking at the complexity of the field, but really to understand the nature of the dynamo. It has plus and minus signs, and this is something we need to understand in full detail. And we now expect there to be a reversal, and we still don't know whether it's really physical and at which distance we should expect this. So more theoretical research, but also observational research is required. So I'm very much looking forward to the chance of using perhaps radio telescopes, maybe even infrared astronomy at much larger wavelengths, like beyond 12 micrometers, would be of really great interest in the future. Thank you.
Questions for?
By having some access to these measures of magnetic helicity, how would it inform you of how the sun operates its dynamo?
So simply the fact that we have two different signs of helicity is, I think, something non-trivial, and it does characterize the nature of the dynamo. It also shows you at which length scales you have the most of the driving occurring. Is it like at a micrometers, or is it even 50 megameters? Is it? This happens when I do raindrops and stuff. I'm talking about megameters for the raindrops. So I think this would be an important aspect of the dynamo already. First the sign, but also the overall spectrum. It would give us evidence that, if I understand your question correctly, that what is behind this is something that is originally conserving magnetic helicity, but it is doing it by putting magnetic helicity into two different length scales. Was that your question, or did I?
Well, you were saying so broadly, it will inform you about dynamo
Yes,
mechanisms.
yes, right.
So could you give us some examples of how it would inform you?
Yes. So, so for example, we don't know at which depths of in the convection zone the dynamo is operating. If it was working at the bottom of the convection zone, we would expect the sign to be of opposite sign. Because there we have expanding motions because fluid is splashing into the bottom. So this would be an example of a dynamo which would have a different signature and possibly also at much larger length scales. That is something that might reflect itself in the overall magnetic helicity spectrum. Mm-hmm. Yes.
So my question is why it's not started from the assumption that there could be some amount of primordial helicity, right?
So you want to build in an assumption that helicity is perfectly conserved?
No, I'm saying why people do not start the calculation assuming that there could be some primordial helicity during the birth of the sun, like in the case of the magnetic field.
So instead of zero magnetic field, you want to start with a finite magnetic field.
Yeah, people sometimes, in order to explain certain solar cycles,
yes.
people have to assume that there was some primordial magnetic field during the birth of the sun.
Mm.
So in the case of the helicity, why it's not the case?
So the maybe I still didn't quite capture your question. I mean, you said you wanted to start with the magnetic field to begin with. Is that what you said?
Yeah.
Yes. So then, right. So then, of course, the fluid motions will change, of course, the structure of the magnetic field. But eventually, the magnetic field will decay unless it is being maintained by a dynamo. Whatever is the dynamo that is operating with the given fluid motions. And so I'm not sure this is necessarily a valuable experiment because it takes a certain amount of time before the dynamo itself can generate its own field. And so you have to get rid of.
But I'm asking, in the case of the dynamo, people have done calculations.
Of mean field dynamos, maybe.
Yes,
yeah.
That there have been primordial magnetic fields.
Yes.
The fossil field which was stored in the sun during
yes.
during its birth.
Right.
So in the case of helicity evolution calculation, why is that assumption not considered that there was some primordial helicity also in the sun during its birth, and then start from there instead of zero helicity or net zero helicity?
Mm-hmm. So I think what you're saying is you want to build a theory which preserves magnetic helicity even at the Babcock-Leighton scenario.
So
also
I'm
not.
just asking why the assumption of primordial helicity starting the evolution of helicity including some primordial helicity of some sign,
okay.
one particular sign.
Right. So I think I need to say that any magnetic helicity implies a magnetic field. You cannot have significant magnetic helicity unless you have also a significant magnetic field. And so, therefore, asking about initial magnetic helicity implies that you have to have an initial magnetic field. The dynamo itself needs to work against it to some extent to build up its own real magnetic field. And so that would be the...
So if there would have been primordial magnetic field,
yeah.
for example, like,
in galaxies, for example, we might have that.
I did in 1970 that assuming there was some primordial magnetic field, and the purpose was to explain certain asymmetrical features
yes.
in the solar cycle.
North-south, yeah.
So if there could be some primordial magnetic field in the sun, why the assumption of some primordial helicity also?
It can, that's right. So you can certainly have that. The question is, what is the importance of that contribution? So,
I was thinking
yes.
that if it could explain something like why dynamo region has negative helicity, but dynamo region has one sign of helicity and corona has.
Yeah, but once you have a primordial contribution, which may well be there, it would have the same sign in north and south, this additional contribution. And then you might expect a certain asymmetry. And there may be indeed, there's already some evidence that there's a finite dipole moment. So there may be such a thing. And whether or not throughout the universe, of course, it's a finite magnetic field is something under current debate. We think maybe there is. Again, I'm still not quite sure what is then the sign of that. Depends on what is more important, baryogenesis or leptongenesis, and one gives a plus and one gives a minus. And by the way, even neutron stars might have a new mechanism of producing, amplifying helical magnetic fields, and that's something we need to talk about, which has nothing to do with turbulence, actually, at least in the late stages. Mm-hmm.
You observe helicity flux in the solar wind and the CMEs and so on. Does that have an influence on the operation of the solar dynamo? For instance, if we would remove these events and not have a corona, would that affect the operation?
So naively, and certainly I said so in the past, that once you don't have magnetic helicity fluxes out of the sun, and that would be potential feedback, the dynamo would not work anymore. That is a simple-minded extrapolation. Now this is somewhat simple-minded because, so let me go back to this important here equation, because the question is, can you have magnetic helicity flux divergencies within the domain? That's the question. Actually, the conclusive was here already. Maybe here. Yeah, this all of this here. So magnetic helicity fluxes will be important somehow, because otherwise we are still subject to this very long, resistively long time scale. So we have to get rid of this. Now, magnetic helicity fluxes can occur even in a closed domain. So if you say that the coronal magnetic fields, you absolutely want to produce a situation where the corona is unimportant, then you have to put a lid on the sun, right? And you can imagine such a situation, at least in a numerical simulation. You make a perfect conductor boundary condition. And the question is, what would happen in such a case? And naively, I would have said the dynamo would not work anymore, at least not on dynamical timescales, because then we are back to this case. And this may be somewhat simplified, because you can imagine situations where you don't have an helicity flux out of the domain, but you might still have significant flux divergencies within the domain. Flux divergencies within the domain. And we have seen that in simulations of accretion disks in a closed domain. So the reason that helicity flux divergencies become important is because we are now in a situation where the shear is important. Shear produces a toroidal magnetic field that is oscillating, but the poloidal magnetic field is weaker than the toroidal field, so there's a strong imbalance between the two. And so the magnetic energy density and also helicity density is varying in space. And so correspondingly, because of this variation, you can have turbulent diffusive fluxes within that domain. And therefore, you might have a situation where the flux divergencies are important even in a closed domain. That is a more complicated answer to that. So the simple-minded picture of might indeed be that the dynamo would not operate if you have a lid on the sun. But in practice, there can be circumstances where even that might not be sufficient. And so the inhomogeneity of the dynamo in the interior is an important aspect to get these fluxes.
So then the dynamo has to shed the magnetic flux also, not only helicity.
Yeah, I didn't talk about the flux, but yes, I mean, no, I mean, I think there are dynamo theorems, of course, which mean that the dynamo cannot be a fast one if you are in a perfect conductor. Maybe you're thinking of such a thing here. Yeah, there could be such a additional connection.
So is the helicity flux from CMEs a large-scale flux or a small-scale flux?
Right. So I think it is. So often people are getting very confused about this question, whether large or small. Because once I talk about small, then all the people get offended who are talking about the best observations, of course, which are all as small scales as possible. But if you think of small as opposed to large, by large I mean the magnetic field that contributes to the cycle, the 11-year cycle or 22-year cycle, then the magnetic helicity flux in CMEs is probably the small scale. Now, on the other hand, we also know that, I mean, the magnetic field is bi-helical, so both positive and negative helicities are being actually shed. And this is encapsulated in the same structure. So even a CME itself, even though it has a small-scale contribution, it might have actually both contributions at the same time. So there are studies by Sarah Martin which show that depending on what aspect of a coronal arch you're looking at, there are aspects that can be associated with positive helicity and other aspects that are associated with negative helicity. So in one of the same structure, you can have both signs of the helicity. But of course, the really important quantity is the small-scale magnetic helicity flux, and CMEs would certainly contribute to that. The orders of magnitude that we are talking about is typically always up to a 10 to 20, 40, 46 Maxwell squared per cycle, per 11-year cycle.
Thanks.
Mm-hmm. Yep, thank you.